Alright, so we're going to look at a couple of our new identities for Chapter 5, which is these combined sinusoids, and we start with our cofunction properties. So if I just begin with my right triangle, and I look at theta, and I define 90 minus theta as my other angle, my third angle, because I know that the angles in a triangle have to add up to 180. And to make that work, that means that theta, 90 minus theta, and 90 equal 180, which is true. And if I label my coordinates u and v, we remember that sine of theta is v, and cosine of 90 minus theta, well, that's adjacent over the hypotenuse, which in this case is 1, because I'm assuming I'm on the unit circle, is also v. Well, I can substitute those, and I get sine of theta is cosine of 90 minus theta. So there's my first cofunction property. I can do similar analysis to get the other ones. If I want to look at cosine of theta, that is going to be u, and then sine of 90 minus theta, the opposite, is also going to be u. So I get cosine of theta is sine of 90 minus theta. Tangent, same thing in terms of cotangent, and the reciprocal trig ratios also work. 1 over sine of theta is 1 over cosine of 90 minus theta from the first cosine or cofunction property, which is cosecant theta equals secant of 90 minus theta. All right. If we think about what's happening with these, so in the parentheses, if I put a value in there and subtract or add it, that translates into a phase shift in my graph. So what I'm really doing is I'm taking the cosine curve and I'm shifting it onto the sine curve. Those are what those cofunction properties are doing graphically. So in terms of radians, cosine of x is cosine x minus pi over 2. But before, we had it as cosine of pi over 2, or 90 minus x. So the question is that really the same thing? And then why is it? Well, it works out if we really think about cosine and sine, we have these things called even and odd functions. And so if I look at my circle, and I define my coordinates, and I go up an angle x, or I go down an angle negative x, I have that u and v, and u negative v, as my coordinates of those points on the circle. Well, cosine of x is u, and cosine of negative x is u, which means that cosine of x equals cosine of negative x, and we define that as an even function. Sine doesn't work quite the same way. So if I have sine of x and sine of negative x, that's v and negative v. If I substitute, I get sine of x is the opposite of sine of negative x. That is called an odd function. And why do these happen this way? Well, if we look at polynomials and we look at the powers, the exponents of them, if I look at x squared, that is going to give me the property of an even function, and then x to the third is going to be the property of an odd function. So let's go back real quick to our argument at the top. And so, are these the same? Why or why not? Well, it works out that cosine of pi over 2 minus x is the same as the opposite of that value because it's an even function, which, if I distribute that negative through, becomes positive pi over 2 minus x, which becomes negative pi over 2 plus x, which gives me the values that we had before. So it is the same thing as what we had before. It's just written a little bit differently. So the phase shift and the graphs are the same thing as what the cofunction is looking at. All right, let's do a derivation of using what we already have about composite arguments, and we're going to get another couple arguments, not all of the ones that are in the book, but we'll get a starting point for it. So we proved geometrically in our handout before that this is true. So if I have cosine of the subtraction of two arguments, I can relate that into cosine A times cosine B plus sine of A times sine of B. Well, if I want to derive the addition part, so instead of minus A minus B, I have A plus B. Well, I do something a little bit tricky, and I write it in terms of what I know, which is subtraction. So A plus B is the same as A minus a negative B. So I expand it with our composite argument for the subtraction, and then I use my even and odd principles. So cosine of negative b is cosine of b because it's an even function, and sine of negative b is an odd function because it is, so I get negative sine of b. I bring down the rest of it, and that negative on the sine of b from the odd function part turns my addition into subtraction as I link them. So that becomes cosine of a plus b. It's cosine A cosine B minus sine A sine B. All right, We can also look at what happens with sine if I'm subtracting two things. And we're going to use what we know as well as our cofunction properties to do this. So I don't have anything how to relate sine where I'm subtracting two arguments, but I do know it for cosine. And so what I'm going to start with is my cofunction property. So that's true via cofunction, cosine of 90 minus a minus b. And then I'm going to rearrange it a little bit. You'll see why in a second. So I'm going to take the 90 minus a, and then I'm going to turn that into addition. So I have plus b. So I distributed that negative through, and now I have 90 minus a plus b. And we have, from what we just derived, a way to expand that. So it's cosine of the first argument times cosine of the second minus sine of the first times sine of the second. Well, if we look at it, cosine of 90 minus a, that's my cofunction property again for sine of a, and then sine of 90 minus a is my cofunction property for cosine. So I've taken the whole thing and now have related it into one line, and the one above it right there, that work for sine and cosine when I have subtraction of two arguments. There's a lot more. We have our handout where they are. We're going to look down the road at double and half angle arguments, but right now this gets us started on our composite arguments.